Hey Tsauce, Titus here. Could you imagine moving without friction? That would be lots of fun, but sadly, it's impossible. Well, maybe for you, but not for electrons. This is due to a phenomenon called superconductivity that arises in certain metals when they're cooled to extremely low temperatures, usually below 100 degrees Kelvin. Good thing we're here in the jungles of Paraguay.
Hey, Tsauce, Tiago here. To put things more precisely, superconduction is a state of matter in which current in a metal experiences zero electrical resistance. Furthermore, due to a phenomenon known as the Meissner effect, external magnetic field lines literally cannot pass through a superconductor. This means that there can't be a magnetic flux through the superconducting loop, so Faraday's law has no power.
It's also good to mention that superconductivity does not conform to the usual rules we learn about in AP Physics C. That's because Ohm's law fails for very low and very high temperatures.
Thanks, Titus. People were almost confused. That was a close call.
That's the power of T. Anyway, how does all this superconducting business actually work? The answer, as is usual with the realm of very cold, is quantum mechanics. When the metal drops below its critical temperature, it undergoes a phase transition, similar to how a liquid freezes into a solid.
It's important to understand phase transitions for this video. Everything in the universe, including me, is lazy. That is to say, it will look to minimize its energy. For a material that can superconduct, the critical temperature is the boundary, where superconduction minimizes the metal's energy rather than the material's regular state, which is why it undergoes that sharp change at that point. For me, the critical temperature is 25 degrees Celsius, which prompts me to turn on the AC.
Nice! Before we can go further, we have to understand what resistance means in terms of ordinary conduction. Observe in this video Ben and Titus, the electrons that make up the current, and Tiago, the positively charged ions that make up the metal wire. Imagine that the jungle is a wire. A sea of electrons flow through the wire, and some of these clumsy fools bump into the ions. This little collision causes the electrons to lose some of their energy, bumping them down to a lower energy state. This is what we call resistance.
I'm a little resistant to movement myself these days. Something special happens after the phase transition, though. It turns out that the arrangement that minimizes the energy below the critical temperature is no longer to have electrons be free, but to have them linked in what is known as a Cooper pair, represented here by Ben and Titus. The reason the pairs form in the first place is that as the electron passes, it attracts the ion a little bit. This ion is positively charged, so it creates an area of net positive charge, which in turn attracts more negatively charged electrons. Usually, the ions would be vibrating like crazy inside the metal and would disrupt the Cooper pair. But since the metal is so cold, they just don't have enough energy. Relatable, am I right, guys?
Cooper pair? Pooper pair. Who cares? I care. Because there's one final piece to this quantum mechanical puzzle. It comes down to the difference between the two major types of particles, bosons and fermions. Fermions are the particles that make up stuff like electrons do. The reason fermions, and by extension us, don't just phase through stuff is because they are bound by the Pauli exclusion principle.
Pictured here is the average fermion distribution. The Pauli exclusion principle means that space on each energy level is at a premium, kind of like NYC apartments. So when one of the fermions wants to come in, it's bumped up into a higher energy level, represented here by the bleacher levels. Bosons, on the other hand, have no such limitations. In fact, in the absence of external agents, they will all chill together on the lowest energy level.
What do Cooper pairs have to do with all this nonsense? Well, as it turns out, when electrons form Cooper pairs, they begin to act like bosons rather than fermions. The electrons in a Cooper pair begin to inhabit their lowest possible energy state. In fact, all the electrons in the current form Cooper pairs, and thus inhabit the same energy state at the same time.
This means that when they bump against the ions, they don't lose energy. They're already in their lowest energy states, so they don't have any energy to lose. They sail along, unhindered by the ions, as if they were ghosts. The resistance has disappeared. That's not all, though. Due to the fact that they share the same energy level, all the Cooper pairs are effectively the same particle and begin to behave as a single macroscopic object as they move through the superconductor. They enter a state known as Bose-Einstein condensate.
At those temperatures, they should call it Froese-Einstein condensate. Brrr. I prefer the jungle. To understand the sheer level of coherence these particles have, we must understand the electrons as propagating waves. Usually, waves, like the ones in the ocean, crash into one another and thus slow each other down. This is resistance. Now imagine if all the waves in the ocean were perfectly orderly and in sync with each other. They would never crash into one another, never interfering or affecting one another. We say that all these waves are in phase. This harmony leads to a total loss of resistance.
Don't let your mind slip to summer vacation just yet. Quantum mechanics is often said to be obscure and disconnected from our real world. But the applications of superconduction have massive potential. First off are particle accelerators, like CERN's Large Hadron Collider, LHC for short, which use superconducting currents to slam subatomic particles into each other while traveling near the speed of light. Next is quantum computers, which require superconduction for their basic unit, the qubit, to even have a chance of working at all.
Bruh. The last and most immediately important of our three applications is the maglev train. Before we can go further, we come to another fascinating property of superconduction, the Meissner effect. This is the effect that superconductors are observed to expel all external magnetic fields and not allow any field lines to enter them.
Why does this happen? A good explanation would be Lenz's law. In the absence of resistance, the material will always be able to perfectly induce a magnetic field via current to cancel out the external magnetic field. This is similar to how a Faraday cage cancels out any external electric fields by inducing an opposite electric field. If you had this idea, however, you would be incorrect. To actually explain the Meissner effect, I would need a PhD in condensed matter physics. Unfortunately, the one I ordered on eBay hasn't arrived yet.
The important implication of the Meissner effect is that it prevents the magnetic field lines from forming the closed loops that are required by Gauss's law for magnetism. This is seen by this magnet that is placed on top of a superconductor. It just can't make the lines flow in a loop from one pole to the other, so that's the only thing a reasonable man can do in such a situation. It begins to levitate. That way, its field lines can form closed loops and everybody is happy.
So that's superconduction. Its future looks bright. The prospect of a room temperature superconductor in particular could revolutionize technology. Cooper, of Cooper pair fame, was himself a Bronx Science graduate. Perhaps the discoverer of the next breakthrough in superconduction is here in this very room.
Okay, we're gonna do it again. We're gonna do another take.